Good afternoon, sir.
Yeah, today's session on week 6.
Sir, can you just like take the concepts and
Yes, sir. It all went over the head, sir.
Yeah, okay, sure.
Yes, sir.
We'll go with that.
Some
With a
important
similar kind, like talking the concept and with example.
Yes, sir. Sir, to be very frank, sir, it all went over the head.
Oh, this week 6.
Yes,
Yes,
sir.
sir.
Okay. Okay, so yeah, we can go with the lecture wise also. We will see what sir is teaching, and maybe I will give a brief intro of that. Then you may
Yes,
understand.
yes, sir.
So my voice is clear and loud, right?
Yes, sir.
Yes.
Okay, so just let me share my screen. Okay, so hope my screen is visible to all of you. Is it?
Yes, sir.
So what we can do, like I have one slide also. So like we can discuss the concept, and then like I can choose your activity question or practice question, or I can discuss with my question whatever I have. So these two things we can do, like discussing the concept, then discuss the question. I will
Sir,
do.
a brief question. Is there any live session in addition to this before submission of week 6 assignments?
Actually on Tuesday there will be a session.
At least we can go through the concept, and if we have any difficulty, then again we can ask
yes,
on
sir,
Tuesday.
even that onto into everything is very confusing, sir.
Okay.
Sir.
And on Tuesday there is a session solve with instructor session. This is today's open session. Last yesterday's session was taken by Susmita, I think.
Sir, in today's session, please discuss the concept so that we can get whatever was taught in week 6.
Okay.
Sir, video lecture is not making it very clear, and I don't know how to apply the concept in examples.
Okay, so
some problem is there, sir. I'm not able to get through the content.
week 6. So yeah, this is the first lecture, and in that taught just brief intro of in bijective, like in week 6 sir talked about how to check 1 and onto. In this video,
yahin pe please can you pause here, sir? Yes, sir. Sir, we are transforming from I am not understanding what is this in line 3, sir.
note that
I understand that W is a vector space and it can be written in, we have created the basis, right? I understand that one is dependent, two variables are dependent and one is independent. So we are putting one by one, first one dependent variable to 0 and then second to be 0, and calculating by adding these two, we calculate the third one. I understand, sir, how the basis is created in step 1. So second step is we are transforming from -1, 1, 0 to 1, 0 and second basis to 0, 1.
Yes.
I don't understand, sir, step 3 because it is a
so
dimension is 2.
What
the
is
dimension
the
is
video? Sir is saying W is a subspace of R3 which have dimension 2 and basis is given here. So he assumed a homomorphism. Saying to be a homomorphism means homomorphism is what? Again a linear transformation. You can now termed as a linear transformation as a homomorphism also. When this homomorphism or when a linear transformation become 1, 1 and onto both, then this linear transformation called isomorphism, or linear transformation means homomorphism. That homomorphism called isomorphism. And in this example, sir just taken the f, what is as defining. Like defining means I have a linear transformation like this. The first image of the basis element of domain equal to the image is 1 0, and the second one is this one. So like he is doing, and just say that this is an isomorphism. So how it is going to be an isomorphism, we will discuss this also. Okay.
Right.
Actually the property is that when, what is the property? If you have a linear transformation T from V to W, okay, and suppose the basis of V is suppose V1, V2, Vn, okay, and suppose the basis of W is, let's say, W1, W2, W, N or M, anything different from N or okay. So if this is happening, then maybe in this case dimension is needed both same. Okay.
Yes,
dimension
yes.
So
It is mentioned in the lecture that dimension is V is also R2 and
R2 and W
W
is
is also. It is
dimension.
mentioned.
So both have dimension same. The property is if T of V1 is equal to, that is a basis element, map to the basis element of W, means W1 or maybe W2 also. But the property is image of the basis element is one of the image of the basis element of codomain. Let's say this is 3 itself or 1 also. Means to say basis image is goes to basis image goes to basis image. In such case, this linear transformation is actually bijective linear transformation. That's why sir has just told in that this is going to be an isomorphism. When the linear transformation is bijective, then it is isomorphism. So why this is going to be a bijective, you can easily do it, not a tough thing. Like why this is a bijective means saying to be need to check the injectivity. Okay, this is needed to check, no? So how to check injectivity? So let's say T of V is equal to 0.
0. That implies
Yes.
V is equal to 0.
So, and see, V is any vector from V, this domain. So, what is the use of basis now? So, this V can be written as the linear combination of basis elements, alpha time, this is V1 plus alpha 2 V2. Like this, we can write, that is the use of basis, no? So, let's say this is alpha n Vn. If V as an event of domain and V1, V2 are the basis elements, then we can write V as the linear combination of basis element. This is the property, or this is the actual definition, you can say. This is the use of basis.
Yes.
Now, what is, now you have that T of V is equal to, you assume that T of V is equal to 0 for to check is that injectivity or not. So if this implies V is equal to 0, then it is going to be injective. This is the mean of you know that in the last in my
Yes, sir. Yes, sir.
also I told you, when this property holds, then it is going to be injectivity. Or differently also, if T of, assume if V1 and V2 belongs to the domain element, and like this, such that T of V1 is equal to T of V2, if this implies V1 is equal to V2, then this is also says this T is injective or 1 or these two are equivalent to saying if this property hold this one is equal to 0, then T is also injective, or differently you can show like this also. These two are equivalent, or if and only if condition have, if this is happen, then it surely this is also, means to say these two are says T is injective. Now as you assume T of, as you assume V is an element, we want to show V is equal to 0 also. So take the image of, apply T on both side here, as we can write the linear combination V as the linear combination of basis element. So here T of V says, Now use the property of linear transformation. The property says you can expand, like expand no means you can make it separate. What is that? T of alpha 1 v1 plus, this is the property of linear transformation, alpha n vn. Now this is the first property of linear transformation. Second property of linear transformation is you can make it out scalar, means alpha 1 t of v1. Similarly, alpha n t of vn, you can make it out scalars. Okay, now this says as you assumed t of v is equal to 0, so equivalently you can say or implies t of v is equal to 0. This left side is 0. Now t of v1, t of vn, as you assumed here, the images of basis element goes to the image of basis element, no, as we assumed. We are proving this here.
Yes, sir.
So is it clear, no, what I am talking?
Yes, sir. Yes.
So as I assumed that
This part are not understood, please.
where this one, okay. So what I in the video lecture, let me show you again. What is that? W is a subspace which have basis those two elements. Okay, now sir has assumed that f is a homomorphism which is also called the linear transformation. Homomorphism means linear transform. Image of this basis element is this one, and image of this basis element means here is this one, and this is a basis element of R2. This is a basis another basis element of R2. So if such case happen, means image of basis element of the domain goes to the image of basis element of codomain, as here is happening. This is a basis element goes to the basis element of codomain. Here is also basis element of domain and goes to the basis element of codomain. If such cases happen, then that linear transformation is bijective actually. So why this is true, we are proving it here. So what I assumed, I have a linear transformation v to w. The domain basis is v1, v2, vn, and codomain basis is wn, w to wn. We are taking the both vector spaces as same dimension. This property holds when the both vector spaces have same dimension. Then that goes to be as a bijective. Then linear transformation will be bijective.
Yes, sir.
Okay. So now as v1, v2 is basis element of domain and w and w2 the basis element of codomain. So what I assumed that linear transformation of a basis element, I just assumed v1 goes to the basis element of codomain, let's say w2, or v2 goes to wn. Similarly, vn goes to, let's say, some vi, or I means from 1 to n is it's running any different from these 1 and 2. Means more precisely, if we write v of I is equal to, sorry, it will be w j. Okay, where j is equal to 1 to n and I is equal to 1 to n. More precisely, in the more precise way, if we write like in the 1 to n, not repetitive form, then it is writing to be like this. This says the image of basis element goes to the basis element. If such thing happens, then we are proving T is bijective. So how we are proving? We took a element from domain. Okay, now as v1, v2 is the basis element of v, we can write as the linear combination v as this form. V can be written as this form. Now we applied T over both sides. Okay, now when we applied here T both sides, so as the property of linear transformation, we can do like this. We can make it scalar out and plus kind of this thing we can write as the property of. And we want to add to show T is a injective, so this property should hold. Means not property, means I assume T of v is equal to 0 and I have to show v is equal to 0. Okay, so as I assume T of v is equal to 0, so I just left right side, I wrote left side as a 0, and this is as the applied after the linear transformation we got after applying this linear transformation. Now these are like we can write as alpha 1. This is a basis element. I just assume as T of V1 is equal to W2. Similarly, all these are the basis elements come. T of W2, somewhere W1, somewhere WK, like this, all will come. So this side is 0. Now you know that basis elements are linearly independent. Nah? Basis elements are linearly independent. These are the basis element of codomain W1, W2, and we just wrote as the linear combination and equate it as 0. So if basis elements are linearly independent, what implies? What is the property of linearly independent means?
Alpha 1, alpha 2,
None of
alpha 9,
the
all are 0.
Alpha
All
are going to
coefficient
be
in
0.
0.
So means what you have means alpha V1 plus alpha and Vn, all alphas are 0, means this is going to be 0, and this is exactly V, our V. So this says, yeah, we got, as we assumed this one, we got V is equal to 0. So this says that T is injective. Now we want to show surjectivity also. How do we show that? Surjectivity
Injectivity
want to
how
show.
we show in matrix.
Use the now if you know the rank nullity theorem, that will be now very easily you can show. If you know the rank nullity theorem of a linear transformation, if you want, I want to skip the
Yes, sir. Yes, sir. We are clear about what is the rank nullity theorem.
very big expression. If you want to skip the big expression, the onto how we will show onto two ways we can say using rank nullity theorem for linear transformation. In week 6, you studied linear rank nullity theorem for matrix. In week 5. In
Yes,
week 6, you are studying in the last video. In this video, here, this somewhere in the last, whatever the rank nullity theorem you are looking. This is the rank nullity theorem for linear transformation. This one. Rank nullity theorem for linear transformation, as you can see. In week 6, you studied rank nullity theorem for matrix. So, if you use here rank nullity theorem, we can also prove, or let's prove by the as traditional way we used to check for the onto. So, what is the onto? Onto says if you have for the general mapping, I am saying if you have a mapping from a set S to let's say A to B, let's say if you have a map from A to B, then onto is definition of general for mapping is for each element in this codomain you should have a pre-image, means to say if let's say B belongs to B, then there exists, this implies there exists an element A in this bigger A such that f of A is equal to B. This is the definition for onto, or checking the condition for onto, if you want to say. This says the onto. Same for the linear transformation we'll do also. If you see, I took last session on 7, I think. If you say very clearly, I just used to check. I spent it 1.5 hour more. Like I spent it to check how the traditional way to check the onto to a linear transformation is onto or not. So like let's check here also for this linear transformation. So we have this thing only, and we want to say is this linear transformation is onto or not. Just now we checked this is into, means 1 1. So assume W is from the codomain. So as we have W and basis of W, this W1 W, basis of bigger W is W1 W2 W2. This is an vector W, small w. So this W can be written as a linear combination of this W1 W2 Wn. This is the as W1 W2 Wn are basis elements. We can write, so let's say beta 1 W1 we can write as the W as a linear combination of W1 W2 Wn. So this is beta 2 W2 beta n Wn. Okay. Now we want to find an element in this V. Sorry, in this V. Yeah, we want to find an element in this V such that T. We want to find element V. Let's say that element is V. We want to find a V such that T of V is equal to W. If such thing is happening, then we are done. So, okay, we have W. I assumed here, we assumed this. Okay. Now you have this, as we assumed that T of W1 is equal to T of V1. So what you can write? Beta 1. T of W1 is equal to, you can write as T of V2. Sorry, V2. As here we assume V2. T of beta 2 W2 is equal to T of W2 is equal to, as we assumed here, V1. V1. Similarly, all will, like, as somewhere will be something. So this is beta n T of, let's say some Wn is also, I am just assuming Wn is T of Vn is equal to Wn. We can assume. So T of Wn can be written as T of Vn. So this is equal to beta. You can now use the property, you can make it beta inside to this T. So this you can write as T beta V2 plus T beta, this is beta 1, this is beta 2, V1. Like this, you can make it inside because of the using the property of linear transformation, T of beta Tn. So now this is the it is separated as according to the operation. We can make it in one single this. So we can write beta n V2 plus beta 2 V1. This is beta n Vn. So you can see that beta V1, V2, V3, Vn is a Vn is a V1, V2, V3 is a basis element of, this is the basis element of V. So if you are writing a linear combination of this basis element, this will give you a vector, right? A vector in V. Assuming to be this linear combination is actually a vector in V. So that means if you assume this is V or V prime, if anything, if you are assume this is a single vector in V. So let's assume this is V prime. So T of V prime is equal to W. So actually you got a V prime in V such that T of V prime is equal to W. This is the definition of onto. As you assume a vector W, you are able to get a vector in domain such that, which is in our case V prime, such that T of V prime is equal to W. So
Yes, sir. Got it, sir.
now this linear transformation, this says this linear transformation is bijective, and as assumed this is a linear transformation, so this is going to be an isomorphism.
May I ask a question here? When you are writing the expression W is equal to beta 1 W, beta 2 W on every one of those, when you get to T of V1, T of V2, you are referring to each basis element of the image being multiplied, is it? Transformed. Each basis element.
Transformed. Each
Okay.
basis na transformed. Whatever the transformed, we got.
Okay. But what's the advantage of doing that? What happens if we actually do the transformation complete one go? Just because in the end, that is what you actually.
Actually, that is we want to try to find a vector in V. We are trying to find a vector in V.
Okay. Oh, you're working backwards, you mean? Okay.
We are working back. We here in forward case, we are going to back.
Okay. All right. Thank you.
Okay. So is it clear to all of you what I'm doing and
Sir,
what
can
I
you
just
take an example?
So this is a simple example. No, this is, if you will say, this is not a theory. This is an example. This is a simple example. Okay. If you want to say, let me take an example. So suppose a linear transformation is from let's say W to R3, or maybe okay, or the same example in video itself. What is that? Where it went? It will be more precise.
Sir, what
what
is there in this line 3, sir? Note that x, comma y, comma z belong to W can be uniquely expressed as
this one con?
yes,
This one.
yes,
Or that, so XYZ can be uniquely expressed as this one. So what I am doing the same thing. No, these are the basis elements.
yes, sir.
XYZ can be written as, if you assume this is alpha, this is beta. So just solve this. This is saying to be this is a vector, can be written as a linear combination of basis element. As here we are doing. Let me connect it.
Right, sir. Got it. Now I got
as here we are doing. If you are, I assumed very good. He is a vector, so it can be written as the linear combination of basis element.
Yes, sir.
So let me take this example itself. T of W is equal to R2. Okay, so where W is equal to x plus y plus z. X plus y plus where x y is z, such that x plus y plus z is equal to 0. Okay, so and R2 is our general case. So we have a basis element.
Sir, may I ask a question here? Sir, in W you have supposed x comma y comma z and this equation. I know that this is a dimension would be 2 because we are going to get two bases, two elements in the basis. Dimension would be 2. Sir, do we have to always calculate this, or we would be given that it is from W2 to R2? Transformation is from W.
Whenever somebody is asked from like this, it will surely give the either image of basis element or whole expression itself. It will be given like that. Like here, if you, I hope to all of you it is easy to find what will be the basis or basis, like any basis, not necessary what in video. You can take any basis.
Yes, sir.
You can find the basis. You can write as x as minus y minus z. So as
video lecture has assumed this thing, but I can write z is equal to minus x minus y. Then the basis would be different.
And given to y as 0 and z is equal to 1.
Yes, yes.
X is equal to minus 1 we get. So one basis element is minus 1, 0 and 1. Secondly, you can give y is equal to 1, z is equal to 0. Then you get x is equal to again minus 1. So another basis element will be minus 1, 1 and 0. So these two will be the basis element.
But there will be 3 elements. No, it is x, y, z.
Sorry?
3 elements will be there.
Three elements.
Dimension is 2 actually.
Dimension will be 2 because when you write this system, this is a equation, linear equation. If you call it a system
Okay,
of
sir, yes, sir, understood. 2 independent are there and 1 independent.
2 independent and 1 dependent. So independent, whatever the independent, you used to give y is equal to 0, z is equal to 1 to get different vectors.
Okay, sir.
So you got a basis element. Anyone?
Sir, what if we have the reverse, means we have given pre-image and image and then we have to find equation?
No. Sorry. Can you repeat again, please?
I mean, if we are given image and pre-image of linear transformation, so how could we derive the function like t of xy equals to what?
So that is okay. Then in this here also we will discuss. in the last session also I very clearly discussed how to find if you have images. Let me go ahead with this. So you have now, sir have given that T of 101. What is the exact? Maybe we'll take T of minus 101 is equal to 0, 1. So T of minus 101 is equal to 0, 1, and T of minus 110 is equal to 10. So this is if you have given. So what will be the exact expression of T? This is the question, no? You want to ask. What will be the expression then?
Yes, sir.
So we will try to find that. So if this thing is happening now, what is happening here? I will reach to here. So again, as I am taking this example, if basis image of basis element goes to basis element, then T is going to be bijective as we proved here. Okay. So here is also the same thing. These are the basis element of domain of this domain W, and 0, 1 and 10, or 10 and 0, 1. This is the basis element of R2 or basis element of R2. So what is happening here? Basis image of basis element goes to basis element, image of basis element goes to basis element of codomain. So in that case, yeah, as just now we proved, so you can say T is bijective. Just now we proved.
Yes,
so this
sir.
is an example to say that, okay, this is the bijective. If such case is happening, then our linear transformation is going to bijective. Now the case is what will be the exact expression? How we will find the expression of T? How we will find? So
Yes.
what is the process like? How we can find? So same in the, I think sir have did also. I will explain how it is happening. Okay. So we want to find an expression in x, y, z term, kind of like when you apply T here, what will be the exact expression? It will give the two coordinates because T is from W to R2. It will be, it have two coordinates, this one and this one. So let's assume a vector from W. So I assumed a vector. Let's say this is a vector from W.
Okay. Before going ahead, can you please brief for a moment what is the ordered basis and the basis which is not ordered? What is the ordered basis? How do we decide whether this basis is ordered or not?
Okay. Okay. I will back. I will go to this.
Sir, can we discuss this first, sir?
Yeah. Okay. I will be there. Let me continue with this. I will quickly finish it. Then that is, I will tell you what is ordered basis, what is standard
Okay,
order.
no problem, sir. Continue with this.
This is the continuing. We are continuing it, so it will be make a continuation to you to understand. So assume that this is a element from W, okay, and we have basis of W is -1, 1, 0, and -1, 0, 1. Yeah, just now we evaluated.
So can you explain the question, please? We are putting a transform on x, y, z and getting something.
The question is, we are trying to find the expression as we have these two images. Image of basis element of domain goes to basis element of codomain as here. We are trying to find the expression. What will be the exact expression as we have the only two separate images of the basis element. So how you will find that, or what is the process, or what will be the exact expression in the term of x, y, z is equal to some 2x plus 3y and 5x plus 3y? What will be that expression?
Yes, sir.
The is it not directly y, z?
So let's see that. Yeah, what I am taking the source example same.
Okay.
What is that expression? Y, z. Okay. So let's find that. So as we just now, we know that this is a basis element, and I assume that this is a vector from W. So
yes.
What is the definition of basis? We can write a vector, any vector in W,
as a linear combination of the
combination
basis.
of this one.
Yes,
As
sir.
basis is actually a span of W, span of W. Basis is a span, can span whole W. So means span means can generate any vector of W. So this is a vector, so it can generate. So how it will generate? Generating means can be written as a linear combination of these two basis elements. And we have to find what will be the exact alpha and beta. I just assume, okay, this is the basis, and suppose, yeah, this is a basis and this is a vector. So we can write as a linear combination of these two vectors. So I just assume.
I have not got step 1, sir. I have got it that we want to find the expression. Sir, you have assumed x comma y comma that belonging to W.
This is a single vector. This is a single vector. Vectors in W are, this is a subspace of R3. Na? So vectors will be in the 3 coordinate wise.
Means we are assuming these from the codomain, sir.
This W is W is from the domain. This domain, our P is from W to R2.
Oh, W to R2. Okay, sir.
So this is a single element, can be written as linear combination. So now solve this expression, and our alpha beta is unknown. We are trying to find the alpha and beta. So this will be minus alpha minus beta and alpha, and this is beta. So we have this equation. If you compare it, both are equal. That means alpha is equal to y and beta is equal to z. Second coordinate goes to equal to second coordinate. Third, this coordinate goes to this third coordinate. Coordinate called as something different than what is coordinate. Third element, or what is that? Coordinate is x coordinate, y coordinate. Okay, coordinate is the y coordinate means second coordinate is y coordinate. Y coordinate is goes to equal to the y coordinate of this side. Third coordinate is equal to the third coordinate. So as we got, alpha is equal to y and beta is equal to z. So what it means that this is a general element. This is any vector. We can give this value. This means these are any vector. You can give 1, 1, 1. This is going to be a vector. That's why we are assuming as a variable kind of. Means to say we are trying to find a general case. You can easily give any value and can easily get the what will be the exact alpha and beta. That's why I assumed a general x, y, and z kind of a variable kind of coordinates. Okay, so that means this x, y, z, this single vector can be expressed as a y time -1, 1, 0, plus z time -1, 0, 1. This is our, when we express this vector x, y, z can be written as a linear combination of this one. What it means that if you assume take a vector from W, taking a vector from W means satisfying this equation. So what will be the vector? Tell me any vector. You can tell any vector. Anyone can unmute yourself and can tell.
1, 1, -2.
1, 1,
-2.
Okay, 1, 1, -2. Okay, yeah, this is a vector from W. So, and I want to write 1, 1, -2 as a linear combination of this one. Alpha -1, 1, 0 plus beta time -1, 0, 1. So no need to calculate each time. Directly you can jump to here. Yeah, I have a general thing. Here your x is equal to 1, y is equal to 1, and z is equal to -2. So 1, 1, -2 can be written as a, this is y here. So means 1 time
1 into 1, 1
plus z time means -2 time -1, 0, 1. So that's why we are trying to find what is the general case here. That's why easy to be not each time have to equate the equation like that too. No, this is a general case and we can just give the value and can directly calculate.
Sir, I want to pause you for a moment. So these -1, 1, 0 and -0, 1. These are the basis of W, that is the domain.
Of W, yes. Now, as you have this expression, as you have this one, as you got here, so apply both sides T. We can apply because this is an element of we assume, so we can apply T. We can find the image of this vector. So applying this side T means apply both sides. -1, 1, 0. Plus z time -1, 0, 1. So use the property of linear transformation. Y goes to y as a scalar working here. These coordinates are real numbers. No, we are taking from real numbers. So these are working as a scalar. So we can make it out y as here. So t time -1, 1, 0 plus z will be out t time. Sorry, t image of z time t. So now as you have assumed, we have already information, this information, as we have assumed already. Okay, we have this, then this t is going to be injected as just now we said. So we have this one, image of this goes to this, image this goes to this. So use this one, -1, 0, 1 goes to 0, 1. So this one goes to 0, 1. This one goes to 1, 0. This is the mean.
Sir,
May I
this
ask
is
you-
not clear, sir. The last step. How it is going to 1, 0 and 0, 1, sir?
Sir, what it is the meaning of applying T on both sides?
Applying T or both sides, sorry, applying T or both sides means I am taking the image here. What will be T of x, y, z means? If you have this one, so that means you have x, y, z, you can replace this with this one, no? The whole, this one is equal to this one. So means this, when I take the linear transformation of this vector means I just replace with this vector with this bigger one. As here, these two are equal. Applying means replacing. That means replacing that vector to be. Okay.
Can I ask a question? I have a doubt where you are using alpha and beta. Can you scroll up a little bit, please? Here you had, in the brackets, you have -alpha, -beta, comma, alpha, comma, beta. We dropped -alpha, -beta because of that not being a reflective number in the codomain, because it was 1, 0 and 0, 1, or why did we drop -alpha, -beta?
So, okay, why we dropped this one?
Yeah.
Actually, our motto is only try to find alpha and beta. As here was easily just we got okay, alpha is equal to y, and beta is equal to z. Otherwise, we can do also x is equal to, we are getting -alpha, -beta. From here, we have to do some more calculation, then we will reach here. But yeah, these two are just directly says, oh, alpha is equal to y, beta is equal to z. And our motto is just finding the alpha, beta. Yeah, we got here. That's why I just drop it here. Otherwise, we have to do more calculation, then we will get. That's all. Nothing different.
So it doesn't matter which combination I select. I can select -alpha, -beta.
Yeah, actually your motto is just finding alpha, beta. So you can, it's your turn, as you want to call it.
So whichever I figure out, I still will come back to this answer. Alpha is equal to y and beta is equal to z for the codomain.
Yes.
Okay.
That's our motto.
Okay. And why did we substitute this back here again? Because we said alpha is equal to x. I mean, alpha is equal to y and beta is equal to z. That's the reason why we substituted back, is it?
And just when we got the alpha and beta, because as we are working, okay, alpha and beta as a variable kind. So we just find the value alpha beta, just substituted here.
Okay. All right. Thanks.
So yeah. Okay, so till here, I think, is it clear to all of you? Because this is already we have given.
Yes, sir.
This one is 1, 0 and 0, 1.
So there is a reason for taking 1, 0, 0, 1, or I mean, I know we've been given, but it could have very well been 0, 1 there and 1, 0 there, or there is a relation.
No, we have given, that's why. See, if you have something given, you have to use, no. If you are
correct, sir.
Not given, so how you will use that?
True, sir. I understand that part, but what I'm trying to say is that they have given just because it works in that the basis here is same as the basis there. That's why this has been selected as an example in
Yes,
this case. Okay.
yes.
Okay, sir. Thanks.
Okay. So yeah, if suppose okay, let me finish then maybe I will tell you the different scenario. Maybe you are thinking different also. Okay, so this is y time 1 0 we got, and this is z time 0 1 we got. Now this is just a simple expression. So this is yz. So what is the expression finally we got? T of x y z is equal to just only yz. Our map is from W to R2. And W is defined as x, y, z such that x plus y plus z is equal to 0. This is our W, this is R2. So, okay, W is subset of R2. So, elements are written as in 3 coordinates, but image is in R2. So, that's why only 2 coordinates we are getting. As the linear transformation is our defined. Okay.
Again, sir, it's only because they were 1 0 and 0 1. If they were different, then it would change, no, sir?
If suppose here is 1, if in it is given like 1 1 minus 1 kind of, so it may be it will tell the difference relation.
Okay, sir.
Sir, could you scroll up?
Okay.
Sir, could you scroll up?
Yes.
Where you are explaining the injective part?
A
bit more up.
No,
a bit more up. Here, when you proved that they were independent, these we must these are all independent, so alphas must be 0. How did we prove that V is 0? Alphas must be 0 because the coefficient must be 0. That is why they are linearly independent.
The all alphas are 0.
Right, but then how did V become 0?
So V is actually the linear combination of V1, V2, V3, where alpha is our working.
Okay.
Yes. As alpha.
Okay, because these V1, V2, and all these are bases.
And all alphas are 0. So if you write the linear combination 0 times some vector, 0 times some vector, each time 0 times some vector, it will give a 0 vector. No?
Okay.
0 times some V1 plus 0 times V2.
No, actually, what I didn't understand was we came from this part where 0 is equal to alpha 1, W1, alpha 2, and so on and so forth. And we proved that since this is a basis of W, then these W1, Wn, and so forth would be independent. And therefore, these alphas would be 0. Till there, I understood. I don't understand how from alpha 1, W1, we shifted to alpha 1, V1.
Okay. No, so how did you get this alphas? Alpha is actually come from this V1, V2, V3, no?
Right.
Alpha
Yes.
is actually the alpha we took from this V only. Then we are reaching to this here and says. So actually our alpha is mainly here, this with the along with this V1, V2, V3. Not
in line.
Okay.
In line above this, there
it's
is
the same alpha. It's the same alpha.
it's
Okay,
the same
same
alpha.
coefficients.
And transformation is being applied on the V1.
Okay, so ultimately we become 0. All right. Yeah, I got it. Thank you.
So hope it is clear to all of you. Okay.
Yes, sir.
So
Yes.
let me tell you a different story that suppose as okay, this is the basis element and image goes to a basis element. Suppose it is not a basis element, it is different from basis element. Suppose this is this means different from basis elements means what? Means suppose we have an image of this one and 2 1 0 minus 2 2 0 minus 2 2 0. Suppose you have an image this one and this one. So these two are basis element, this one and this one.
Linearly dependent.
These are linearly dependent. These two
multiples.
Are multiples. So these two are not a basis element. So we have a case that we have an image such that this is not a basis element, Okay, yeah, this is an element of this our previous one, but you can say that these two are not forms a basis, so these are not a basis element, or means to say in different word, image of two vectors is given like this. Okay, image of two vectors, just saying to be, we have this vector, image of this one is this, we have this vector, image is this one. So in such case we are able to find exact p. So the answer is no. It is very difficult to find exact p. The reason is, whatever we did operations here, because of only these are the basis element, that's why we are able to do the operation.
That is why it was the assumption.
That's why the assumption. If those are not basis element, it is very difficult, or I will say not exactly, you are unable to find the exact linear, what is the exact expression.
And it won't be 1:1.
On to
1:1.
It may not be 1:1.
Two things from domain are going to same place, is it?
Actually, this will not be a linear transformation itself.
Okay.
Yeah, the reason is you can easily prove here. The reason is, as this is given to this one, okay, t of -1 1 0 is equal to 1 0 you have, and second one is -2 2 0 is equal to 0 1 you have. So what is that? You can make it out to here. So t time -1 0 -1. You can actually prove this is not a linear transformation itself. So -2 as 2 into t -1 1 0 is equal to this equation. I am just becoming ahead of this equation. This implies this one. Okay.
2, 0.
So that means 2 and image of this one is given as 1 0 equal to 0. So this implies that 2, 0 is equal to 0, 1, which is it true? Never. It is absurdity. This is contradiction. So actually this is not a linear transformation itself.
Yes, sir.
So how you will find the exact, means what is the expression? There is no mean of asking expression.
There won't be any relation. Yeah. Okay, sir.
So I hope you got the idea why we are able to, when we have the basis element, then we are able to do the all things. Otherwise,
Yes.
it's very difficult to do all.
Sir, over here we are saying that the image of the basis is the basis, right? In the image. So this is a sign of checking subjective also. Or, what is the use of this? I mean, what are we really doing?
Isomorphism.
This
Is
is
it
going to be
isomorphism?
We
It's
proved here the second one also, no?
Yeah,
How
both 1:1 and 1.
It will prove both. It will prove isomorphism.
Yes.
पूरा सम का 164 164 होगा.
I muted to all of you. Okay. So let me go with the video part. So I told many things. I remain to ordered basis and standard order. Okay, so yeah, let me tell you, that is a very important. What is differences in ordered basis and simpler basis? Okay, so suppose you have a like same W, our W is here, X, Y, Z. This is a subspace of R3. Okay. This is a subspace of R3. And we found the basis of it. What we found? -1 0 1 and 1, sorry, -1 1. So we got, this is a basis of this W. See that this is written as, if you have a set, let me tell you, if you have a set and like this, 1, 2, or maybe not 1. A, C, D, B, F. Something is like this. If you have set like this, okay. So what it means that you okay, you in the first math one you studied only just set, and you studied that this is and A, B, C, F, B. These two sets are equal. Huh?
Yes.
You know that these two here the order is not mattering here, no?
Yes.
These two sets are equal.
Yes, sir.
As you see in math 1 or math 2 also you are dealing with the set. So, but suppose the condition I made it, A I wrote here, this is the first place, this is the second place, this is the third place, this is fourth, this is fifth. Whatever I fix the places here, it will come to A will always come to first place, C come to second place, this is third, fourth, fifth. Whatever I fix the now what I said, I am fixing here the order. Order means here fixing the exact place. A come to the first place, B come to the second place. So now a different set I am making. A come to here first place, but B is here, C is here, F is here, B is here. So as D is in third place and C is here in second place. So in order case, these two sets are not equal. Because I just now I fixed that okay, A will always come to here in the first here as here is written in the set form, whatever expressive form is written, this is will come in the first place, this is the second place, this is the third after a comma. I just fix it. So in this case, these two sets are not equal. I just fixes the order of the each element. So mean to say when you have a set and that set is an ordered case as here. Okay, I just made a set here. So and fixes the each element the position. So this is an ordered set. Like here I am making A, B, C, D, E, F to till Z. So you know that after A, B will come, after B, C will come. So assume to be in order, or if your number you are writing 1 to 10, this is 1, 2, 3. After 5, the 6 will come. After 6, 7 will come. After 9, 10 will come. So this is if I am writing in this form with the order fixing form, in fixing an order. So now I am writing like this 1, 3, 5 till 10. Each element is containing 1 to 10. This set also containing. So, but this is not in order. Means I am not fixing here. Not fixing means this set is different from this one. So when you have a set and you have just fixed the
Can you come again, please?
Okay, what I'm saying here, if you have this set, this is comes like this. I have another set 1, 3, 5 till this set also contains 10 elements as here. So if I am just fixing order means okay, one is come first as here, one first place, second place, third place. Here one came first place, but 3 comes second place, 5 come third place. So these two are different set in case of order. When we say ordered set,
Okay,
elements
okay,
are coming as a ordered kind of.
Okay. Thank you.
Now the same thing is happening here. If you have this set, if you have this basis element, if you have this basis, so I am fixing this is the first place, this is the second place. Suppose I am fixing here minus 1, 0. I just make it as first place here. This is on the second place. So and this first place element come as the second here. So in the ordered case, these two sets are different. This is also a basis. This is also, as you know, it will satisfy, it will generate the whole R2 because in this set, it can be written as linear combination of. And here is the same, this is also generate because containing 2 element and containing the same, as you know, the linear combination can be written as each element can written as the linear combination of these two elements. I just fixes in the when I'm fixing the order of element in this set only. So this is a basis, but ordered basis.
But how does it make a difference in the transformation? It's still going to be the same, correct?
No, so it will transformation will be the same. It will affect on the matrix.
Okay.
What
but
is of this ordered basis is when we will try to find the matrix representation of a linear transformation, then we needed the ordered basis.
So we can add them and multiply them. If they are in order, then only it's possible to, if there are different equations, to add them and multiply them will become easier. Is that must be the reason for ordering, no?
No. The reason is when you are writing the linear transformation in matrix form, you are fixing the elements in this form. No? You have expression. If you have gone through the video lecture, I will tell you how we will write. So actually, you are fixing the elements in this order.
Yeah. So the
order of basis elements.
So there are multiple equations now.
We needed this ordered basis.
So the multiple equations can be combined only if they are in a particular order, is what I'm thinking. Yeah. Matrix, what matrix does is
But I can always change the order by exchanging the columns and multiplying it with -1, isn't it?
But you will start with an order, then only you will interchange.
With the order, you are not multiplying here with the there is nothing multiplication, just the elements order. Ordering the element, not
if I exchange any columns, will there be a change of sign? No,
not will not change. Sign will change. It will change these two entries. Means entry somewhere will change. It will come to first here, then here. Or if you are changing the order, it will come to here and it will go to here. In the same column, it will lie in the same column, but will change the position in the same column. You will see that.
I'm writing the basis vectors as columns or rows.
So let me tell you. Let me tell you how we are writing a linear transformation in the matrix.
Sir, one question here. Sir, how is 1,0 and 0,1? These are ordered basis. If we write the other way around, then they are not ordered basis. How do we decide?
So this is an ordered basis. You said this is an ordered basis. Means, yeah, okay, I am fixing it order. I am saying the another ordered basis is this one. Another ordered basis is this one. So the question, it will be like this. The question is, I am writing here. We have a W. Suppose we have a linear transformation T from W to R2 with we have T of -101 such that T of -101 is equal to, what is that exactly? 0, 1. And the question I'm writing, T of -1, 1, 0 is equal to 1, 0. I have a linear transformation.
Defined like this.
Boundary properly. Defined like this. Defined like this, or such that this is okay. And then question is, find the matrix representation of this linear transformation with respect to ordered basis. Ordered basis with respect to ordered basis for domain. For this domain is, I am writing the order here, -110, -101.
Okay.
With respect to ordered basis for domain is this one, and for codomain, because this is one basis for domain, for matrix needed ordered basis for both domain and codomain, and for codomain this one. Okay. The question is, we have a linear transformation defined like this, find the matrix representation of T with respect to ordered basis for domain is this one. For domain is this, and for codomain is this. I am writing the another. This is the first question. I am writing the another question is T is a linear transformation from W to R2 such that the same property as we have given. This is the same here. Okay. The question is find the linear transform. Find the matrix representation of linear transformation T with respect to ordered basis for domain is this one -1 0 1 -1 1 0 and here for codomain is let's make it here the same for codomain, or maybe different. We can change the order also. So what I mean to say, you can see here the basis element for domain is this one comes first and this one come on the second place. But here for domain, I changed the order here. I just said find the domain ordered basis here. Ordered basis for domain is this one. Means I just changes the order here. So these two are now different questions. Only you can see the difference is this one. Just changes the order. Only this order. Now these two are different question. It will give a matrix representation different. These two give the different matrix. Numbers entries are the same, but the position of the entries will differ. We will see it here. What is the differences? So how we will find the matrix representation of a linear transformation? The question is. So as we just now find the expression P of x, y, z. Just now we found here. P of x, y, z is equal to
YZ.
YZ. Here the order is not till finding the matrix, order will not matter. You can easily find, okay, we have this image, okay, and till finding the expression, it will not matter to you, okay. So this is YZ. I will tell you if you have a difficulty, let me erase it here. If you have a difficulty, you can change this box with such that P of x, y, z is equal to yz. And here also I am changing with this. I am changing this box. If you are getting difficulty, why not matter? So I am just simple expression I am giving. Find the matrix representation of, we have a linear transformation this one, or we have a linear transformation this one, such that the expression is given. Find the matrix representation of T with respect to this one. So if you have difficulty with this box, means what will be the expression, because this box will help you to find this exact expression. I just changed. Otherwise, that's why I just chooses to be more maybe question, maybe it will be like this. So if it will be like this, then first thing is you have to find the expression, then you will able to, or from here also, okay, maybe let me erase this one. Maybe you may confuse. Actually, it makes very easy to solve this question. I will tell you why. So the question is, I have slightly changed. That is makes very easy. The question is this one. I have a linear transformation with the expression is given here. Find the matrix representation with respect to the order basis for domain is this one, for codomain is this one. And also I am erasing it here. I have the same question with the same expression. The same, only the ordered basis is
order is different.
Now let's solve the first question. I'm solving a first question. We have this expression. Okay. So how we will find the matrix representation? Finding the matrix representation means you have to find the images of order. So how we will find the matrix representation of a linear transformation is find the image of the first element of order basis, yes, of the domain. So what you will get here as you have expression?
1 0.
Now find the image of the second element.
This is 0 1.
Minus 1 1. Oh,
1
no.
0.
What is there? Minus 1 0 1. Sorry.
Yeah.
Minus 1 0 1.
0 1.
What will be the image here? 0.
0 1.
Now the thing is, okay, I found the images of each basis element. Now this is a vector in R2, and this is the basis of R2. So actually this, if you assume, okay, you are looking that this is the element of this set itself, but if you think as this is a vector and this is a basis, so you need to express this vector as the linear combination of this basis. So let me tell you. So actually this can be written as this ordered basis. This is ordered basis. So this can be written as 1 times 1 0 plus 0 times 0 1. Correct?
Yes, sir.
Yes, sir.
This is and this one is again you will think that okay, this element is from itself from this ordered basis codomain, but think as this is a vector and this is a basis, so you can express this vector as a linear combination of this ordered basis.
Okay, we have to express this as the linear combination of
this order,
the basis of the codomain.
Codomain. That
Yes.
means if you express it here, 0 times 1 0 plus
1.
1 times 1 0.
and 0
0 1.
0 1, sir.
0 1 times 0. So now your matrix is exactly what will be. Now write this. This is the first image, and write the expression. The entries of this matrix will be this coefficient. In the first row will come 1 0, and the second column will come as a for the second image of codomain, second image of element of domain. This is the image is this one, and write the coefficient. The matrix representation of this linear transformation is this linear transformation with the disordered basis here is given is this one. Okay, see, you have to write the order of this one also in this order. You have to write the expression in this order. This will come as 1, this will come as like in this order 1 0 then 0 1. Not it will be like this 0 times 0 1 plus 1 times 1 0. You have to write a proper order of following the order. That's the use of ordered basis. You have to write in this order only, whatever the order here. This is 1 0, so it will come as a first place. This will after the plus, it will come as a second place. Okay, as here is again same thing.
Can you please expand this matrix? We got the one matrix. Now, can we express this as a matrix multiplication and getting as a result the other the domain? It can be expressed, no, sir? Like AX is equal to Y form.
Actually, this is the use. Why this? What is the use of this matrix? Is actually this T of X Y Z
can be expressed in
something is written like this, so you can actually get the exact image with the multiplying any vector writing to be linear combination. Something I will tell you that is a more means this exact expression or this exact P of 1 1 1 something is there. It can be directly written to be here 1 1 1, but it will be here the coordinates will come. It will be more thing like it can be exactly evaluated with the matrix multiplication. That is the use of finding the matrix of a linear transformation.
Okay, I was thinking we can see it there because you've just taken coefficients and put them a matrix, but we can see those matrix multiplication in the previous two equations. So we could probably straight away write the matrix now itself from what we are seeing on the screen. So if please correct me if I'm wrong. For example, we got 1 0 0 1 here. Now that is actually a matrix multiplication of the 1 0 0 1s, and
No,
it
no, no, no,
leads to
no, 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 no. This is not
not
matrix.
correct.
No, no, not correct. Matrix is actually comes from this coefficient, not the matrix multiplication of 1 0 or something.
Because
This
they
is
are the x and y now. So
no. So actually, this is not come as a matrix multiplication. This comes
okay.
as a coefficient. I think to be the coefficient in this
This
column.
so what I'm trying to say is this is the coefficient matrix of a
Linear combination,
multiplication.
as a
Yeah,
linear combination.
yeah, and we can see the linear combination above, isn't it? So
Above,
the t minus 1 1 0 is equal to 1 1 0 plus 0 0 1 is actually the linear combination along with the second one.
yes. Okay.
No, that I don't think that is the case.
Okay, then I'll
Okay,
need
so
to understand that better.
let me tell you the difference why why the orders is now effective. Now I have changed. I have taken the elements are same, but order is you can see that different. So what is again? So if you are trying to get that, so you will find the image of the first element. Here is -1. Here the first element is this one. Not here you can see that the this one was. The image of the first element -1 0 1. What will be again? As your expression in this here is also the same question is with the same expression. Okay. So the again yz word will come here is 0 1. The images are will come same. Okay. So you can write this as a linear combination of this here. So it can be written as 1 0 time 1 0 plus 0 time 1 time 1 time 0 1. Okay. Now t of the second element -1 1 0 equal to it will be 1 0, and if you express in this order it will be 1 time 1 0 plus 0 time 0 1. So now the matrix, if you will write here, the matrix will be
0 1
0. This is 1 here,
1 0.
1. See the differences. Once you change the order, see the differences. What is happening? Entries will same, entries number will same, but yeah, they will swap somewhere. Like here is swap here. It will come in the same column, but yeah, it will be it is swapped because of that order.
Okay, but what is the benefit of this? Like, is there any particular importance to this?
No. So I am giving the importance of order only.
Okay.
If order varies, then sir has shown the difference in the which we have obtained.
Let me clarify. In a real life application, does this matter? Because when we actually fix our transformation matrix, that's going to be that, right?
Yeah, actually it will matter when you try to find the eigenvalues and eigenvector. Then it will
Okay.
Will effective.
Okay.
When you will see in MLF.
Okay.
So here I am just giving the what is the effect or what is the use of order. Why we are saying ordered basis. So if someone is giving with the order saying to be this is the order. So order means it will affect on the entries and number will the entries of what will the numerical value of entries will be the same, but it will be changed. The changes will be places of the numbers will change. As here is swapping, or maybe if it is in the 3. So let me tell you an example here. I have an example. Yes, will tell you more precise. Like this is the question. Which of the following is the matrix representation of the linear transformation? This again see the word with respect to the ordered basis is here beta and in the standard ordered basis, okay, standard ordered basis is remain to say. So standard ordered basis of R3 for domain and codomain respectively. So beta is the domain for this one, and standard order basis is for this one. So it still remain to the what is the standard order basis. I told you something about ordered basis. So whenever somebody says standard ordered basis means the standard ordered basis of for this course I'm saying we know only a standard order basis for R. You can say R, R2, R3, Rn, till Rn. So we know the standard ordered basis for R1, R2, R3 is for R1 is only 1 here. Because you can actually use it to remember if you are saying this is actually a fixed thing. Standard order is a fixed thing.
1 0 and 0 1.
1 0 and 0. For R3 1 0 0.
You mean to say that in the
0,
first
1,
position
0.
we have to place 1 and then keep on
0,
shifting 1.
So similarly for Rn it will be like this 1 and rest all are 0. Still n coordinate will come here. Coordinates will come here. The second element will be 0 1 0.
So we are shifting 1.
Something like EI. Something like what we used to write EI.
For me, your voice is breaking, or all of your, like my voice is clear, no? All of
Yeah,
Yes,
your
sir.
voice is clear, sir.
So this is 1. So we know only standard ordered basis for R, R2, R3, Rn, till Rn we know, and those are standard ordered basis for R2 is this one, standard ordered basis for R3 this one. If somebody says this is the standard order basis 1 0 0, okay, and 0 0 1 1 0 1 0. So this is not a standard order basis, okay. You can see the elements are same, but order is different. The third you can say this should to come here and this should to come here. Or this is not a standard order basis. This is
but this can be an ordered basis.
This can be. You can say okay. This is a ordered basis. Okay, I'm saying okay. This is an ordered basis. Okay. It can be ordered basis. Any basis can be an ordered basis. Means I'm just said okay. This in this order I am following. For this question I will follow this order. That's all. For this question or for a particular question, somebody says ordered basis means for that question I will follow this order, and that basis is called, you can say, ordered basis for that particular question.
Right, sir. Now got the difference, sir.
Okay.
Yes.
So this is not a standard. Standard order basis is fixed thing. This one for this R3 is this only. Apart from this, anybody says different, so that will never be a standard order basis. For R2 only this one. For Rn, I mean now we can give to n any real number, so this is going to be an order. Standard order basis.
Right, sir. Now got it, sir.
So these are the differences in order, basis, ordered basis, standard order basis. So ordered basis means for this question I am following this order. For suppose beta is given like this 1 minus 1 1 and 1 1 minus 1, I just changes here. So and minus 1 1 1 0. So suppose this beta is erased here and this beta I am following. So the question is same. So what it means that I am following this ordered basis for this question. Okay. For apart from this it will, but for this question I am following this order. That's the main thing to be ordered basis. Now hope to clear to all of you what is the use or what is the mean of ordered basis. For a particular question I will follow this order. For different I will follow different order. Means as they will give us. The question is
So here this is standard ordered basis of R3. So we will take 1 0 0 0 1 0 0 0 1.
So it
Okay.
is understood that previous one whatever I said.
Okay. Okay.
So what will be now matrix? Till now, whatever we discussed, is it clear to all of you? If you are still have doubt, you can refer to that previous whatever you have. You can stop me and say to back. I will go there and again tell you what is there. What is your doubt? Discuss again.
So second one is the correct. We have to do x plus z, y, and y plus x to get it, no, sir? So
okay, you are getting to someone.
yes.
What or not? You can post in chat if you are getting your number. Okay, option 2, option 3, or you can unmute and tell also.
There's one point I missed again. I was asking earlier, do we write this basis as columns or rows?
Column.
Columns.
Whatever the coefficients you got, you will need to write column in that order. The first one will come in the first, the above or most, below that, below that, below that, exactly like that.
And I think too.
Okay, so let me do it there. So again, we have the expression this one. The matrix will be first find the image of first element of the domain, of the basis element of domain. So this will be T of 1 minus 1 and 1. So it is minus 1 and 0. Okay, we got this image. We need to we have to express this image because as T says, T is from T goes to R3 to R3. So actually this is an element of R3 and says this is a standard order basis of R3, means we can express this vector in this. So ordered basis is here, our standard order basis is 1 1 0. We can express this vector as a linear combination of these vectors. So if you will try to express, you will get the same here. Quickly you can do here. It will be minus 1 here. 0 0 0 time. Okay, so the matrix will be, now this is the first element, so it will give the whatever the expression you got, it will give the first column here. So the first column will be 2 minus 1 and 0. Now find the image of second element of the basis. This is minus 1 1 0. So image will be here as it is giving minus 1, and this is 1 here, 0. So again, if you will express here, you will get minus 1 time 1 0 0 plus 1 time 1 sorry 0 times sorry 1 times 0 1 0 plus 0 times 0 0 1. the second element of the basis of ordered basis will give the second column. So the second column will be -1, 1, 0. Now the third
So
column.
can you please adjust your mic? Voice is somewhat low, sir.
I hope now it's loud.
Yes, sir. Yes. It's okay now.
Okay, so now the image of third element. Okay, 1, 1, -1, 1, 1, -1. So this is.
Isn't it -1, comma 1, comma 1 in the previous one?
-1, comma 1, comma 0.
1, comma 1. Y plus z, no?
Y plus z. Y plus z. Okay.
Sorry, sorry. Y plus x. Y plus x.
Y plus. Oh, sorry. Y plus x. No.
Yeah, it's -1.
Okay. So it gives 0. So image will be 0, comma 1, comma y plus x, again 0.
Yeah.
Sir, you erase it.
Here too. What is that? 1, 1, -1.
Sir, -1, 1, 0, you
Sorry, here
erased.
2 will be. 2 will be, no?
It is correct, the top part, no? You erased. T -1, 1, 0 is equal to -1, 1, 0 is there.
Okay.
That
Yes.
line.
Okay, so now it will be 0 time 1, 0, 0 plus 1 time 0, 1, 0 plus 2 times 0, 0, 1. So the third column will come as for the third element. This will be 0, 1, 2. So this is going to be.
Sir, could you show the question again?
So because we had standard ordered basis,
Yeah, actually,
it was
now
redundant.
I am now changing here. It will be interesting. Now I am erasing it here with this standard order. I am just now erasing. Now it will be tougher. So I am erasing
Yes,
with.
sir. I didn't even do that step because I thought, I mean, I missed, but yeah, if it had been different, it will become, we'll need to
So
now calculate.
and I am writing 1, 0, 0. So I am giving a basis 1, 1, 0. And the third element is 1, 1, 1. So
Sir,
actually,
if it is not the standard, then it will be given now.
It will be given.
Okay, sir.
So I just erase it now. I am giving the question is the same here. Please see carefully. The same. The changes is for the codomain. The basis is changed now, and basis is this one. Now what will be the matrix? I don't know here what will be the option. You will tell what will be the matrix. I'm making the fourth circle here, and this will give the your answer. And you will tell the entries you people. So everything will work till here. The changes will come here. This portion.
So how will we proceed then? I mean, because now we will have to do 2 into 1, 0, 0 plus -1 into 1, 1, 0.
So actually now now you will see the use of system of linear equation.
Yes.
Okay.
Till here, okay, everything is fine. Just writing the all things. But now you will see use of system of linear equation.
We'll have to solve for it.
For each time you have to solve. Like what you will get here. Now you got this one. So what is the next step is, see, I also don't know what will come the coordinates or coefficients. So you have to assume, okay, alpha time, let's say this is 1, 0, 0 plus beta time, the second element 1, 1, 0 plus gamma time 1, 1, 1. So let's now you in the this will give a single vector which is alpha plus beta plus gamma. It's the first coordinate, second coordinate will come beta plus gamma. Third coordinate is gamma. So what you have 2, -1, 0. So you have this equation. And for that, you have to solve, to get alpha, beta, gamma, you have to solve this equation. So let me erase all, see that what is going to be. So that means
Gamma
now
is
we
0.
can do the quickly. Gamma
Yeah.
is equal to 0. Sometime
Beta
maybe,
is equal to
see, if you have a bigger expression here, alpha plus beta plus gamma something, so you have to solve the equation. Yeah, but in quiz and all, you will not get like a big expression and have to solve it. It will be easier.
up to this much we can do, sir.
So there will be three systems we'll have to solve.
So three equations, three systems you have to solve each
Will
time.
become 3 columns.
It will give the three equations. So each time
Three systems.
Three system. Each time you have to solve three systems.
Alpha, beta, and gamma.
Another, and the next one is another. So actually, if you have a rhythm, you can, like, if you do the more practice, you can do quickly. You can do very quickly, because okay, what will remain here, like here gamma is 0, you got, and beta plus gamma is equal to -1. So gamma I have 0, so beta is equal to -1. Okay, now alpha will be alpha plus beta, and gamma is 0. So as here we got alpha is equal to, okay, alpha I have, beta is -1. So let's say -1, gamma is 0 itself. So it is equal to 2. So alpha
is equal to 3.
So that means your first column will be, as your alpha you got
3 minus 1
3
-1 and
-1 0.
Okay, now what you can do, you can make it erase it here quickly, and like 0 1 0, the second element is here is given, so you can erase it like very quickly. If you have, you can solve the equation very fast only while looking the all. When you have do more practice, I'm saying on the practice we can easily solve the system, and each system have unique solution. In this case, I'm asking from you why it have unique solution.
Because it is in row echelon form, sir.
No, the proper
Because
word.
it's a basis, so it has to have.
Basis, okay. So, but not a. When you have system of linear equation have unique solution.
When the determinant is not 0.
Non-zero of the coefficient matrix.
Yes.
Okay. So when you have non-zero determinant non-zero, so when you form a system of linear equation, like what it means to say, when you form a matrix using these vectors, actually when you solve this, it will give a, what is happening here, if you write the coefficient matrix, what will be here? Just looking till here, you can please tell me what will be that by looking very quickly. It will be
1 1 1
1 1 1 and
0 1
1 and
0 0 1
0 0 1. So see that what vectors are coming here, the basis vectors are coming. See that here, this one, basis vector, and basis vector is coming, and as you know, these vectors are independent, and in such case what will be, determinant will be
non-zero.
So it is a upper triangular matrix, and determinant is the product of diagonal entries.
So
determinant is 1.
These are the regions because the basis elements are linearly independent. So when they will come as the coefficient matrix of a matrix, coefficient matrix of a system of linear equation, then they have a non-zero determinant, and in that case you have a always unique solution. So each time you will not get like when you solve this kind of problem, when you got three equations, each time you have always a unique solution, so that you will able to put the entries quickly, and means able to put the entries uniquely.
Okay, sir. Got it, sir.
So I hope you got now. For the second time, you can do it. Is I'm leaving to you. This is the only
Yes, sir. Yes, sir.
calculation part.
We can discuss the next topic.
So here, I think, is it clear to all of you? So I have the next. Now this is all about in this first lecture. The second lecture is imagine kernel is removed. Let's discuss that. I think
Yes,
we can
sure,
discuss that
sure,
also.
sir.
Okay, so okay, so what is in in that video? Okay, let's see that what is in that. You will know about the kernel and image space. What is kernel? What is image space? And these things already. So see that this condition f is going to be 1 if and only if kernel is going to 0. So kernel. Okay, let me tell. I will tell you the definition. And range space range. Yep. These are the big expressions. What is happening here? If you will see clearly here in this scenario, sir is talking about what is the relation between of a kernel and when you change a linear transformation in matrix form. So what is the relation when you like in the kernel is comes as a word for linear transformation, and null space, in the week 5 you have gone through in week 5, no? Yeah, null space. In week 5
Yes, sir,
the word
yes,
null
sir.
space is there.
Yes.
So what
Null
is the
space.
relation between the null space and kernel? So null space for the null space, this is, suppose this is the linear
Matrix.
transformation and this is the matrix representation of this linear transformation. So what is the relation of this kernel and null space of this matrix? Here in this video sir is talking about here, whatever at this time stamp. And next is on the image. So on the image, what is the relation in the image of T and column space? Column space, if you've gone through week 5 episode tool of a matrix, what is the relation in kernel and the column space of a matrix? So what we have, so kernel, suppose you have a linear transformation from a vector space V to W, then kernel of a linear transformation is the collection of
all V
vectors from domain V such that P of V is equal to, say, this is the kernel. This is the exact definition, if you will say. If you say, this is the kernel, this is the definition of, means collection of those vector, collection is the, kernel is the collection of those vectors which give the zero image, gives the zero image. And image space the just collect the all the images of, means TV.
It means the range of the codomain, right?
Or you can say range of the linear transformation.
Yeah, range of the linear transformation.
Collect the all images. That's all. That is the image of TV.
Excluding 0, no, sir?
No, including
0 is also in the range.
Including.
V belongs to this V.
Okay. So it
For all
includes.
V, collect the all image. That is the image space.
Okay.
And actually, if you see in video, this kernel is subspace of this domain V, and this image is subspace of this
codomain,
this codomain, this W. And whenever you have a subspace, you can find the basis of that is a subspace. Similarly, you can find the basis of kernel. And image space, you can say image or image space now. Image space is also a basis, sorry, a subspace of this W. You can find the basis of this image space. And when you have a subspace, you know, and this is the one word, and the another word is when you have a subspace, it have a dimension. So dimension of this kernel is called nullity of T. And dimension of this image space is called rank of T. Rank of T. Here the rank is for the linear transformation, not for matrix. So our T is here linear transformation. So this is the differences in week 5 and week 6. In week 5, you read about the rank for a linear, for a matrix. For a matrix. For in week 6, you are reading about the
rank of
a linear transformation. And similarly, nullity you studied for
matrix.
The null space for the matrix. Here is the nullity reading for the linear transformation. That's why they see words are same. Why? Because the reason is there is a relation between this nullity for this linear transformation, and whenever you find a matrix representation of this linear transformation, let's say A, and if you find the null space of or nullity of this matrix, both are same. That's why you can say the word is, in other word, you can say the words are, we are using here the same thing. Because when you find the matrix representation of this T, whatever the nullity will be of this matrix, it will be the same for nullity of this linear transformation. And the same here, whatever the rank of this A will come, A is the matrix representation of T. So whatever the rank of this matrix A will get, it will be exact the same rank of this linear transformation. That's why the rank words and nullity word is we are using the same here for matrix and for linear transformation. It is clear to all of you?
Yes, sir.
Yes, sir.
Sir, sir, for range T is equal to TV.
Range T, okay,
T is equal to TV, such that V belongs to capital V. So it is for all V or
all V.
All V.
All V. This is not a particular. This is using your general case. No? So this says the definition of image in set form. It says that collect the all images. Collect the all images of T. So this says all images. V is belongs to V and TV. This definition itself says okay, I am collecting all images.
And all images from the range of the transformation.
Actually, this is exactly the range of T. In other word, you will say range. You know, there is a difference in codomain and range word.
Yes.
A function. Range is exactly the collection of exact the images, and codomain is that set called. If you have a function f from set S to T, or let's say from A to B. So here your domain is A, codomain is B, but range is exactly the image of
f of A.
That is you can say f of A. In other words, in set form, exact collection of images. So here your image space is exactly you can say TV, this bigger image, the collection of all images.
Sir, I have a question. Yesterday we were told that the rank of a transformation plus the nullity of a transformation is equal to the dimension of V.
Yes.
So
exactly the rank nullity theorem.
So basically we're saying then when we find the matrix of the transformation, it will have as many columns as the dimension of V.
Yeah. So for the rank nullity theorem for matrix is the collect a number of columns.
Yes. And you are saying it would be the same for the matrix of the transformation, that rank plus nullity.
You can see that why it's happening. let me tell you. Okay, I will tell you the relation why we listen. See, okay, so if you have a matrix of m cross n, rank nullity theorem says rank of, suppose this is the A matrix, rank A plus nullity of A equal to here n.
Column.
Yes.
And if you have a linear transformation from V to W,
Yes.
so rank nullity theorem is rank of T plus nullity of T
T will be equal to dimension of V.
of this
V.
domain.
Yes.
V.
Yes.
Why? Because now when you find the matrix of this T, this matrix representation of this T,
yes.
Suppose I am writing dimension of V is n and dimension of W is m. So what will be order of this matrix? This matrix representation I am saying. This matrix. Order
I know the columns will be n.
Columns will be
n.
Okay. How?
So, sorry, columns will be the dimension of V. I don't know what the dimension of V will be.
Let me tell you what is happening. What we are doing. Why the matrix is right. I am now the more like we solved with the example. Now tell you the theory. What is happening here? So now let basis of V is V1, V2, Vn. This is the basis of V.
Okay. Okay.
Let basis of W is W1, Wn. W1, W2, Wn.
Okay.
Sorry, m is here, dimension is
m.
m.
Yeah.
Wn. So this is a basis of W. Not only basis, let's say ordered basis now. Whenever we talk about matrix, we needed saying to be ordered basis. So V1, V2, Vn is the ordered basis of V. W1, W2, Wn, Wm is the ordered basis of W.
Okay.
Now, what we are doing, we are trying to find the image of each basis element. So find the image. So T of V1 is equal to, I don't know what will the image. Let's say this is W. So what now next is you have to find the linear combination of in terms of this.
Yes.
Right?
Yes.
Let's say alpha 1. In the matrix form I will write. This is suppose A11 W1 plus sorry, it will write okay. So A21 W2 plus A31 W3 like this. A M N W N. Okay, I just wrote it. You will see that what's happening. Now need to find the image of second element V2. So I don't know. Let's say now
it could be any other W.
Any element. So let's say okay. So I am exactly writing the linear combination.
Yeah.
So it could be
A21.
Sorry. A12.
Yeah. Sorry.
Just assuming I can actually give any number. I am just writing order A11 because of that.
Yeah.
A1 W1. A1 W1 plus
A22.
A22 W2
plus
right.
A32.
No. Here will be m. No?
A3. Oh yeah. M2.
M2. What is that in matrix form?
Yeah, AM2. AM2.
Okay,
AM2.
let's see that something. AM2. Okay, we will see that. AM2. Something will come. We will see that.
Second column. Yeah.
So like this, T of Vn till Vn we need to find, and something will come. I don't know what will come.
Yes.
If I will write again, I will forget.
Yes.
So now the matrix will be like this.
It will be a m by n.
A11, okay, A21, A31,
M1, AM1.
AM1. Yeah. A12, A22, this will come here, A32, I think. Similarly, AM2. Yeah, correct. Now the next for the third one will come. Similarly, third for fourth one till for n will come.
Yeah, AN1. No, A. 1n. Yeah, sorry, A1n. 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 A1.
Now I
Can
stopped writing, not erasing. Just 1 minute. Okay.
A1n.
Now
A1n.
A1n. It will come to
Go to
M.
Yeah.
So you can see that matrix when you
Will
write
be
the
M by
matrix,
N.
it will become a
M
M
by
by.
N.
Now see, now if you write the rank nullity theorem for this matrix, then what will be rank of, let's say this is B, I am saying matrix representation of this T is this B, which is in short used to write like this. T, if you will say this is beta and this is gamma. So the proper ways in the book, you will, if you will see, it will be right like this. This is called the matrix representation.
Beta is the basis of what? Sorry.
This is the beta is the basis of domain.
Okay.
Yes.
And gamma is the
for codomain. So writing like in the book form, I'm saying, if you'll see, if you read
this
any
is
book,
how we write the matrix of the transformation.
Like this. It used to be right. Matrices look like they will write like this. So this is beta is for domain, gamma is this. This is exactly equal to this matrix. Now write the rank nullity theorem for this matrix is rank of B plus nullity of B, as you know the number of columns. So n.
Yeah.
So see the relations as here you for the matrix.
Yeah, that's why it's coming to dimension of V. Okay.
So, and this is how for the general case writing to be the matrix representation of a linear transformation.
I've understood. If only I can retain it.
Okay, so this is how.
Sir, I hope you will be sharing this PDF.
This is in the Word. Okay.
Yeah, whatever. If you could please share it, then we remember it as it is.
Okay, but Word, I don't know how this WordPad. This is Note, no? This is Notepad. How I will.
I'm sure it can get converted to PDF. All of them do.
So save as option would be there. Save
Yeah,
as
yeah, it would be there. Please, if you could do it.
In this, so many rough I have did.
That's okay. We understand. We understand.
Otherwise, we have to watch the video once again, sir.
Okay, okay. I need to be right in the.
It's okay.
Sir, what you've written at the last is really nice. This is what I'll be able to retain as it is. Otherwise, I'll forget.
Sir, can I add one step to this? I asked that question before. If I can, so there now we have a matrix of A's, which are coefficients. If I multiply this matrix by a column starting from W1 to WM.
Okay.
Could you do that, sir, please? We represent it as this. Yeah, and here we say W1 starts with WN, ends with W.
Right. Okay. Oh. Okay. Okay.
Now this will be equal to a column matrix T1 TV1 starting is TV1, ending is TVN. Is that correct? That's what I was trying to understand.
In the earlier.
Yeah.
What is now? If you are what I'm
it
saying.
Becomes a.
So if you write the multiplication, the matrix multiplication is exactly T of V1. The first multiplication, or maybe what will be the order of this multiplication? This will be sorry, this is M here. So M cross N. So you will get a matrix which is
N sir. It's N rows. So it's W1 to WN. Because TV1 is going up to TVN, so W1 is also going up to WN in number of rows. Last row we haven't written, so that's why it's coming.
Okay, no, it is something. This is W1. This is still WM will go. No?
Yes, sir.
Yeah.
Yes, sir.
WM. Correct. But it's is it becoming a sum?
Problem is this is not a coordinates. So multiplication, I forgot to say these are not coordinates. This is a single vector. So it will come like this.
Oh,
It will come like
okay.
this.
They are not scalars.
These are not scalars. So this
it,
will
sir.
not come as a so this will give a matrix with a different order.
Got it,
It
sir.
will be of m and no, it will be a different thing. It will be a different thing.
It looks so much like matrix multiplication, but now my doubt got cleared, sir. Thanks.
These W's are vectors or matrices?
No, vectors, no.
They are vectors.
Yeah,
Okay.
that's why I see interpreted with as a matrix multiplication. So no, see, it will not do. We will not do like this. So actually, there is one thing when yeah, I will back that. I will. So I hope you got the rank nullity. What is the
Yes, sir.
okay? So I was now the rank nullity. Let's back to the rank nullity. Then I will tell you next thing is okay. So you got what is rank, what is nullity, and what is the relation, why we are using this same word with the linear transformation and for the matrix also. The reason for because of matrix representation of the linear transformation. Now the question is, you know the definition of kernel also, you know the definition of image also. So there may be some question. Like for this question, I'm just saying, if you have a linear transformation, this one, so what will be the kernel of this linear transformation? Okay. Okay, Sridhar is saying, sir, too much for today. Okay.
If v is equal to 0, you can find for that.
TV is equal to 0. Okay.
And v is x, y, z.
So how? Yeah, that's the question here. That's the this thing will come in the lecture 3. How we will find how do you are solving? What will the exact kernel T? Okay, this actually this will work here. Yeah, but I will tell you 2 ways. This way is also work, but I will first tell you the lecture way, and then I will tell you this way.
Then
okay. So what is the process to find the kernel of T? Yeah, how we will find the kernel of T? Anyone solving this? Is it, or may I have to be proceed with the solution?
Yeah, trying to solve, sir. Trying to solve.
Okay, let's wait a minute. Okay, I will stop soon. Yeah, I'm just looking.
Maybe it's a little late to ask this question. In the previous one, it read as 2 bases. Can you go to the question, please? I'm just trying to remember that. Here, you can. What I'm saying is, which of the following is the matrix representation for linear transformation T? What would be the expression with respect to the order basis, beta and order basis? So there are 2 bases that are given, right? Standard basis, and then there is the ordered basis.
So actually,
why am I trying to find out the transformation between beta and standard basis?
No, I didn't get your doubt.
Can you scroll back up? It's related to the first question, actually.
Okay.
Now, with the transformation, I got 2 minus 1 0 minus 1 1 1. That is the transformation that has come. Okay, but why am I doing that for the ordered basis and then trying to find out what the standard basis is going to be, combination is going to be?
No. So standard order basis itself an ordered basis. Is that out? No, I didn't. Okay.
No, from the ordered basis. From the ordered basis, am I trying to get the elements of?
I think it's because one is for the domain and the next one is for the codomain. The earlier example that sir told, the f of the one was expressed in terms of a combination of the domain, sorry, codomain. That's
beta
why
corresponds to domain, and then standard
it's
basis
given there.
corresponds to codomain, is it?
Yeah, it's written there.
Okay. Yeah, actually the reason is I got your point. Maybe I didn't get your question. So actually what is that? See, you are looking for these bases are same. But the differences is for the whatever we are getting different. See, for a vector space, we have infinitely many bases can possible.
Right.
Like for R3, for R2, you have infinitely many ordered bases. You have infinitely many bases. So, like in that we are fixing standard ordered basis is 100. This is also a basis of R3. So for domain we are taking this ordered basis, and for codomain we are taking this ordered basis, or if you are assuming this or the standard, whatever you.
Okay. Okay, and I'm writing this basis as column vectors, right?
So expressions after getting the image, getting the image, we expanded that vector in that basis or codomain basis of the after getting the image, express this vector as the linear combination of basis of codomain, and then coefficient we are writing as column wise coefficient.
So coefficients are column wise, but the elements themselves are of row wise, is it? Because
no. Rows are not coming as there is no importance of row. We are writing the coefficient in column wise. Whatever the rows come, okay. I don't know whatever the rows are coming. I don't know as here. I don't know this is the first row. There is no relation in. I don't see any relation. My relation is writing the column wise. This is the main concern. I don't know what is the effect coming on the rows. So don't care about that. No need to concern also. What are the relation or what are the effects are coming on row? No, we needed only whenever we are writing row the column wise, and yeah, this is I needed, which is comes as a coordinate.
Yeah. It's R3, no, so it's 3, so x kind of x, y, z. So x is first.
Maybe if you can help me with the transformation that was there. Okay.
Sorry.
No, when we do the transformation for 1, -1, and 1, it is 2, -1, and 0. For transformation of -1, 1, 0, it's coming as -1, 1.
No, you were right when we are discussing this full proper thing. So we got the image and properly wrote. So why you got again confusion? I don't know.
Because I'm trying to work on a sample problem and somehow I'm not getting the answer. That's the reason. Okay. Fine, I will catch up with you later. Thanks.
Yeah, actually, let's proceed with it. Actually, we spent it on time lots of time we spend it very slowly. So maybe if you have doubt, you can rewatch again and maybe try to solve your exact question what you have.
Sir, yeah. I want to make a submission. OneNote has export as PDF option, sir. You can export as PDF from there.
Okay. Yeah, sir, sometime there is not much written in the petition, so that's why. Okay.
No problem, sir.
I will.
Sir, can you show the page where you are showing the rank and nullity, where you have explained that? Yes, sir. Sir, can you show this map? Sir, you have taken A11W1 plus A21W2 in the first row. And the matrix we have written as A11, A12. When we multiply this matrix, sir, what are we getting, sir?
No, not multiplying. That is the wrong thing. Just don't forget. Don't ask that. We are not multiplying anything.
Sorry, it was my miss.
That is, we are not doing anything. There. That was a mistake. That C got clear.
No, it's sir, on screen. If this is the first of all, this is the A11. You have written matrix B as A11, A12, and so on, up to A1n. Okay.
Yeah,
you have written. Oh, okay. You have written this. I was.
Oh, no,
thinking
no.
that
So
this is the
this is
multiplication.
not a separate matrix. These are the columns.
Okay.
You
Okay.
got
Okay.
confusion because of this.
Yes. Yes.
These are the columns, not a separate matrix of multiplication. These are the columns. This is another column. Okay, so let's move to what I had here. So I was discussing about.
Sir, kindly complete the topics which were discussed in the lecture, sir, so that.
Oh yeah, lecture wise I am going. Lecture wise I am going.
Yes.
Lecture wise. So yeah, actually in that I told you what is the in this video for week 6, what is sir is telling, what is the relation, whatever just now I discussed here. What is the relation with the matrix or whatever the columns are coming with the whatever you have this images. Let me make it bigger. So what is that in that video sir is talking about in the second lecture, what is the relation with the matrix and null space nullity kind of will work here. Let me show you. So actually this also, and ahead thing is also discussing how to find the basis for kernel, which I am thinking to discuss till here. I will discuss that, and it will be very clear with the single example. And let me discuss, then I will connect with the video. First solve this example. Let's solve this example. So the question is, I want to find the kernel of this linear transformation.
Only the zero vector.
Is that?
But sir, if it is a linear transformation, then of course zero vector would be there, and zero goes to zero. So one of the options is always there.
So one option is always you will get a kernel zero vector will be always. Okay, but I needed some extra. Maybe
yes,
there are vectors.
Yes. How do we check whether there are some more or not?
So that's the thing. That's the we'll do. So actually for this question, the null space is I think 0. See got no? Okay. Yeah, actually it will be null space will be 0. Let me check that y is equal to 0. Is equal to 0. Yeah, actually let me change with this. Then it will be good. For this question, or maybe for next question. 21. Let me change that. Maybe. Then it will be more clear because the null space for that is only the 0 space. So it will not affect any. Whatever I want to do, that will be with the lecture, video lecture. So let me erase with this expression. X Z Y. This is 0. This. Okay, for this we have this expression T of X Y Z is equal to this. Now what will be the kernel for this linear transformation? We want to find. So the first thing is, according to the video lecture, now let me write to the next page. I wrote here too many things. We have a matrix, linear transformation x y z is equal to x plus z y and 0, and t is from R3 to R3, and the basis is, let me quickly write here, 1 1 minus 1 minus 1 1 minus 1 1 1 minus 1 1 0. This is ordered basis, minus 1 1 0 1 1 minus 1. 1, 1, minus 1. For domain and standard ordered basis for codomain. And we want to, the question is, what is the kernel of T? This is the question. We have this question. So how do we solve this? The first thing is, according to as in video lecture we will go, and that is actually the more general form. That's why sir have discussed, because sometimes those things will not work what we have this kind of. It maybe sometime work will not work also. For the image space it will not work. So let's go with the general case as sir have did. What we used to, somebody is asked with this question, what is the approach we will do or we will follow? The first thing is, you have to find the matrix representation of this linear transformation. So now tell me, what will be the matrix representation of this linear transformation? Quickly you can do, because for codomain I am taking a standard ordered basis.
So here beta is for
This is
domain.
For domain.
Domain and standard
For codomain.
This
Beta is for
codomain.
this one and standard for this one.
Okay.
-1, 0.
-1, 0.
Yeah, it's fine.
No matrix and okay. Okay, I'm solving. Okay. So what is then next is so if this is on
-1.
the standard ordered basis, that means just you are writing to be like this 100 plus
It will remain the same.
so it will work
Remain the same.
remain the same. Yeah. So it will be
Same.
2 minus 1 0, and for -1 1 0 you will get minus 1
-1, 1, 0.
minus 1
-1, 1, 1.
1. No, 0.
Zero.
1, 0. Last one, 0.
-1 1 0. And for the third one, 1 1 1 minus 1.
0, 1, 0.
0 1
0.
0 1. So we have this matrix. This is a matrix representation of linear transformation with respect to beta and standard, as I am making it as. Yes. So now the next step is, you have to find the null space of this matrix. In week 5 you have studied how to find the null space of a matrix. So means you have to make it in reduced row echelon.
RREF, yes.
So this is 1 going to be, or if you want to change it with the -1 and make it change with the R1 R2, whatever you want to do, you quickly do here. What is that? 1 minus 1 here, and this 2 minus 1 0 0 0. What I am doing? Okay, can anyone tell that what I am doing here? Okay, this is -1 1. This is 0. And, oh. So this is here. What I am doing here? R2 minus 2 R1. This is going to be -2 1 -2 2.
So the result is RREF is 1 0 0 0 1 1 and
So
0
first
0.
operation what I did, I just interchanged, okay, the first and second rows. So this is -1 1 1, sorry, 1 -1 1 2 -1 0 and 0 0, and now multiplied with the -1. So this one is here, -1 with the R1. So this will get, and now the next one is same as it is. Now what I am doing, R2 minus 2 R1. So is this my calculation is correct?
Yes, sir.
So I still remain to, this is in row echelon form, reduced row echelon form I needed. So it will be 1. Now what a R1 plus R2. So it will be 1, 0, 3, 0, 1, 2.
Sir, the first row would be 1 minus 1 minus 1.
This one. Oh, I multiplied with the here. This one. 1 minus 1 minus 1. Na?
Yeah.
Right.
That's
So
okay.
it will be. I added here, so it will be 1. Is it correct now?
Yes, sir.
It should be -2 in the previous one, isn't it? 1 minus 1 minus 1. 0, 1 and -2, isn't it?
No. So
correctly. Sorry.
No, it will be 2. It will be 2 because time I will add it here. No, minus will plus. Okay, so now this is in reduced row echelon form. So what will be now if you are writing to be as a system of linear equation x1, x2, x3? So it have two linearly. How many?
It would be one dimensional.
Linearly independent and two dependent.
Yes.
Yes.
The dimension would be 1.
Dimension would of the null space means nullity of this matrix is 1.
Yes.
Now, what is the null space of this? The exact null space.
Exact null space.
X. So what, then write the equation.
x1 plus x3 is equal to 0.
X1
so
plus
x1 is equal to minus x3.
And
x2 plus x3 to x3. 2x3 is equal to 0.
Or if you write it here, it will give you to x1 is equal to minus x3, and this will give x2 is equal to minus 2x3. So assuming 2x3 as 1, so x1 will be minus 1, x2 will be minus 2. So the vector will be minus 1. Minus 1, minus 2, and 1. So null space of this matrix is this one. No?
Right, sir. Yes.
And nullity of this matrix is 1. So 1. Now you got the null space of the matrix representation, whatever you got matrix for this linear transformation. So next step is I want to find the kernel, which is also you can say kernel. No? So next step is whatever you got here the null space, just write like this. You will connect with the video easily when you will see that. You will connect with the video. What is that? Then will be -1. Just 1 minute. I'm missing something. Okay. Okay. So the next step is whatever you coordinate you have this one -1 multiply with the first element, because we have basis for beta is for domain. So our kernel, okay, I am getting here the kernel of okay, basis of kernel. Okay, once we got the basis of kernel, we will get the kernel itself. Okay, so okay, the question is what is the kernel of T? Okay, and the second is asking the basis of kernel of T.
1.
No,
sorry, basis was -1, I think.
No, so this is not a basis. Whatever you got here, now remain to multiply with this basis. That's why the next step is this basis. Whatever you coordinates you got here, so -1 time the first vector 1 minus 1 1, this coordinate, with the second one minus 2 times minus 1 1 0. I will show you video, then you may connect with the minus 1 1 0. And the third one is this one, 1 time this third vector 1 1 minus 1. So what will be the exact? This is a single vector. What will be that? This is minus 1 plus 2 plus 1. So 2 will come here. Now minus 1, it will come 1 minus 2, 1 minus 2, and 1 here. It will be 0. The next one is minus 1, 0, minus 1, minus 2 will come. So you got this vector. So this is the basis of kernel of T. This is a single vector. So as just now I told you, you got nullity of this matrix representation, this matrix. So nullity of this matrix, let's say this is A equal to, just previously I told you, nullity exactly with the nullity of linear transformation. No, nullity of the matrix, whatever matrix representation, will be exactly equal to the nullity of the linear transformation. So you have nullity you got for matrix, for this one you got 1. So nullity of the linear transformation will be 1, exactly 1. And as you got the basis also 1, single one, basis of the kernel is single element 2 0 minus 2. So as you got nullity 1, so you got also basis for the kernel also. Till here clear is to all of you?
Yes.
Okay. Now I didn't find, like, this is the basis of kernel. This kernel can be written as a in the some expression xyz kind of. My question is some in this form, like something in this form. So what will be that expression?
Y
so
equal to x plus z.
Actually this expression can be got from this here quickly, from here itself. This is x plus z. So you know that kernel is the collection of T of v is equal to 0, where v belongs to collection of those v such that T of v is equal to 0. That means you need to equate it as equal to 0. 0 means 0 0 0. Is it? So if you equate it here equal to 0 0 0, that means x plus z is equal to 0, y is equal to 0, and 0 equal to 0. So you got y is equal to 0 and you got x is equal to minus z. So if you write the kernel, so kernel of T is exactly equal to x y z such that x is equal to minus z. If you want to in this form, in this expression, if you want to write in this expression, and as I just told you how I am trying to write with this basis, using this basis in this form kind of, with the equation kind of in the form of equation. So okay, whatever I followed the process, that would work for the finding the basis of the kernel.
Yes, sir.
Okay. Once you got the basis, from here itself you can infer. I just told you this a quick way. This is just I just told you this is a quick way, as here I was discussing. It will work to you. So this will give you a quick way, basis in this expression form. But what will be the basis here? So basis can be found using this way only. Find the matrix and do the all things, do this, write this expression and find the basis here. Using this basis, you can exactly evaluate this. See, you have this expression and kernel is, what will be then kernel? I have this basis. What is the use of this basis? you have this basis means I need to be find means this the kernel will be the linear combination of this vector, right?
Sir,
Where alpha
yes, sir.
belongs to real number. If you write like this, it will be 2 alpha 0 minus 2 alpha. Alpha belongs to R. This is x coordinate, this is y coordinate, this is z coordinate. X is equal to 2 alpha, y is equal to 0, z is equal to minus 2 alpha. Is there any relation in x and z? X is equal to minus z. So kernel of t is equal to, if you write in x, y, z form, such that x is equal to minus z. See, using that
you mean to say that from using this method, first we derive the basis of kernel, and from the basis of kernel, we arrive at the expression of the kernel. But we can reach expression till the expression of the kernel from the very first thing which is given to us.
Very first, directly from here.
But from here we will not get the basis.
Basis, yes. Basis will be, if you want to find the basis, you have to go with this way.
Right. Now I got it. I have one doubt.
So,
sir. In the last line, suppose the null space. The null, we have found the null space. So can you scroll up a little bit? We have found the null space. This null, the dimension of null space is 1, right? Suppose the null space is 2-dimensional. So then
suppose, okay, I'm writing here. Suppose you got another vector, minus 2, 2, 1, something.
Yes.
So using the first one, you got a first vector. Using the second, you will get the second vector of the basis of kernel.
Okay. Then the basis would be 2-dimensional.
The second vector, how you will get? Using this coordinate, this numbers, minus 1 time that vector plus that vector, right?
Right.
So you will get second vector. So let me erase it. It will be
okay, sir.
Clear?
Yes.
So let me continue.
Sir, we found that the basis is 2, 0, minus 2. So this would be the basis of the kernel, or can we also say it could be 1, 0, minus 1?
So best ways, yeah. So actually,
would it be 1, 0, minus 1?
Actually, in such case, whenever such kind of thing is happen, suppose you have a 2, 2, 2 as a basis. So just divide with this 1, 1 also a basis. This is also a basis. So actually 1, 0, minus 1 is also a basis.
What about, sir, minus 1, 0, 1?
Minus 1, 0,
0,
1.
1.
Yeah, actually this is also a basis.
In week 5, there are so many questions.
So all of these can be considered as the basis of the kernel, right?
Because in a vector space have infinitely many bases. All these can be considered as basis.
So in a way, we could have derived it from the first transformation expression
actually,
itself.
Using all these, you will derive the same expression. This one. See that you can easily derive, assuming to be this x, this is y, and this is z. So x is equal to minus 1, y is equal to 0, z is equal to 1. There is a relation, yes, x is equal to minus z. These all will give the unique this expression. This one, single expression. All will give this unique expression. Okay, so don't worry with this number. A vector space have infinitely many tests.
Okay.
Tells you the.
Sir, in the end, have you found all the set of all the zeros for this kernel?
From? So actually, this is the collection of all zeros. You write the expression here. No? You can easily check that. See that how it is. T of x, y, z is equal to, we have x plus z, y, and 0. Okay. Now you have a relation. This one, no. It is the collection of it is collection of vector which have this relation. X is equal to minus z, means x plus z is equal to 0, and y already we have 0. Okay, if you want to make it 0, so actually this tells you this is the collection of. Did you got? No, I just quickly told you, no.
Yes.
Maybe you missed that.
Yes.
See, okay, what I am saying, this is you have the expression. So this x is equal to minus z means x plus z is equal to 0. Okay. Kernel means I want to find those vector which gives 0. So if you substitute here, let's take a vector satisfying this one. What will be? Actually, I missed one thing. Oh, in that I missed something. Oh, in this set, you got y is equal to 0. No, here I just missed.
Yes, sir.
Plus z and include this one also. Y is equal to 0 with the comma. I just missed it.
Yes, sir. That's why I am not getting.
Oh, sorry. I maybe made a mistake. So it will be set form x plus z or x is equal to minus z and comma y is
equal to 0.
This is the whole set. Oh, I missed that. So you have y is equal to 0 and it's satisfying these equation. Collect those vectors. Now tell me any vector. It will be, let's say, satisfying. Tell me a vector from this kernel, from this set. I'm saying.
Okay,
1 minus 1 0. Oh, sorry, 1.
Yes, 1 0 minus 1.
1 0 minus 1, or maybe 5 0 minus 5 will come like this. So if substitute here, it will give 0, right?
Yes.
This is the collection of all zeros, give image of 0, gives 0 image. Clear? So now tell me, let me tell you, let me relate with the video lecture. What is here happening? So what is here? So what these things tells you in here, sir is telling about what is injective, what is kernel, what is the mean of this kernel, tells you 0 means definition of kernel, or this is when the function is injective. In that case, kernel is going to be 0 subspace. So you will see that easily when you solve some problem. You will see that when a linear transformation is injective, in that case kernel always will be a 0 subspace. So I want to tell you that whatever I just now discussed, this exact here. What is that? What is the title of it? What is here written? Image null space and kernel and null space. Kernel and null space. So what is happening here? Sir is telling about when you got a null space.
Actually, sir, this is a theory sort of thing, and
no,
difficult to relate.
That's why I want. That's why I'm discussing here. That's why I want to discuss whatever I did here. What is the relation with this video lecture? That I want to tell you. See, whatever we did here, here, these things are actually told in this theory part. Why this is going to be 0? Actually, this is here you are proving it. Why this is happening? Here we solve with an example. Why this is happening. But here we are proving it with the matrix Aij using as here these are entries of Aij form. So this is the matrix representation of a linear transformation. These are the Ij's, entries Ij's, A of Ij, something whatever he has. And what is the relation with this is the vector, basis element of codomain W1, W2, W3, as here you can see W1, W2 something. So why these going to be 0? Why we are multiplying here? D1 W1, W is equal to D1 W1. D1 is actually D1 is Aij, Cj something. Maybe. Yeah, actually this is a theory part
yes,
of it.
Yes, sir. It is little bit difficult to understand, sir.
It is actually, if you will see that, it may be little tougher. Yeah, whatever we are doing, whatever we did here, this is the story.
Okay, sir. No problem, sir. Actually, I can watch this video once again.
If you watch now again, maybe after looking this, what we are doing here, after doing some example, if you watch again this video, not only this video, in this video, actually, sir have solved some exact example in this video. Here, if can see that sir changed the matrix representation in reduced form and then find the basis x1, x2, x3, assuming to be as a T. Then next is here find the null space of this matrix.
Yes. Till null space it is clear, sir.
And then what he did, he multiplied with the 9, this whatever 9 with the E1. E1 is the basis of that beta, whatever we have. 3 multiplied with the, wait, let me stop here. 3 with the 9, 2, 1 in 9, 3, 0, 9, 4, like this. Sir have multiplied, na? One vector he got. He multiplied with the second vector, this one, 1, 2,
Yeah,
minus
yes,
1, 0.
we have already discussed. We discussed here, sir.
So these things, similarly for the second example, he is doing the same thing here. Okay. So these are the sir have taken W as here and try to solve. So if now watch again, you will be very much clear.
Sir, I think all the concepts have been discussed in all of these 3 videos.
I still remember in this 3 video, the all concept for our today's session still remain for the find the basis of image space.
Yes,
we
sir.
found till here the kernel for kernel.
Yes, sir. Yes, sir.
Remain only the basis, finding the basis of kernel. We also discussed the rank nullity theorem also. So that part is done. So let's stop now the session. Whatever
Sir, if you discuss it now, then it would be over, sir, and we would be able to do all the practice assignments and all.
I don't know. So it may be, see, it is now approx 2 and 2 hour and 42 minutes.
Yes,
Now
sir.
if I will discuss, it will go 3 hours and 30 minutes. Maybe it will really go
Sir,
apart.
can you arrange one session tomorrow so that we can assimilate what we have been taught
Last
today?
session will be, there is another session also on Tuesday. So that will be like a with this kind of solving with this and maybe solve with instructor.
Okay.
Kind of.
Sir, have you updated it in the calendar, sir?
It is in calendar. Let me see.
There's session on Tuesday, sir.
It is Tuesday.
Actually, it is not in the calendar, sir.
No, it is in my calendar. It is.
Okay. I can see it it is from 8 to 10.
8 to 10. Okay.
Yes.
So let's end the session for today.
Yes. Okay.
Whatever we at least discuss, it may help to solve the problem.
Okay. Thanks a lot, sir.
Thank you, sir.
Thank you, sir.
Thank you so much,
Thank you, sir.
all of you. Now, still remain some time for the day. So have a nice day. Apart from.
Okay. Thank you once again.
Thank you, sir.
Thank
Same to
Thank you, sir.
Same
Thank
to
you
you,
so
sir.
much, sir.
So much.